So welcome to the Egeria Webinar program. This is a regular event that we have most months. We're re-establishing the program after the summer break to have one on how to build a native repository connector. We've then got a couple of subsequent webinars, one in November and one in January, around repository proxy connectors, how to use and then to build them. And then we're into what you do after you've built a catalog next year. So without further ado, Chris, do you want to tell us about how to build a native repository connector for Egeria?
With pleasure. Hey everybody, Chris here. I'm just going to walk us through this presentation to indeed do exactly that. So talk about how we can build a native repository connector specifically for Egeria. Thought would be useful to get us started is, if I highlight the right screen, is to talk a little bit about some of the different options for connectivity. So when we talk about connecting to metadata repositories within Egeria, there's sort of 2 to 3 sort of fundamental options. So the first one is something we call an integration connector. And these are about providing the ability to exchange metadata with third-party technologies. So you could think of this as a way of integrating things like existing metadata catalogs, or even other tools within the data ecosystem, whether those are databases, BI tools, those sorts of things. These have their own particular way of running through something called integration service. So they follow a slightly different pattern than what we'll talk about today. But just to call out that those are one option. What we'll talk about today then covers sort of the second option / third option, which is a repository connector. So repository connectors give us the ability to integrate directly into a metadata repository. And they really come in 2 different varieties, native connectors and adapters. So I'll just briefly cover the difference between those 2. Native repository connectors, and this is what we'll talk about in much more detail today, provide us a way of directly implementing the Egeria APIs in order to store metadata, specifically according to Egeria. So typically they involve creating their own persistent store of that metadata. And generally they will support any type of metadata within the Egeria system. Now to contrast that slightly with an adapter repository connector, these are, again, more of an interface typically to a third-party metadata repository. They tend to operate at a much lower, much more granular level than those integration connectors we covered just a second ago. And oftentimes what you'll find is that they may only support a subset of the different metadata types. So they may not support all, let's say, 800 different types that exist within Egeria, but only those that are relevant to that particular repository. So hopefully that makes sense at a high level, the different types of connectivity options. And again, what we'll dive into in detail here is specifically the native repository connector. I know there's only a couple of us on, but feel free if you want to interrupt for any clarifications or any questions. Otherwise, we will progress forward. Okay, so as I said, we'll dive deep here on native repository connectors, and I'm going to try to do this in sort of the classical peel and onion approach. So we'll start at sort of the highest level, we'll delve a little bit deeper, and we'll just do that layer by layer. So at the most fundamental level, to implement a native repository connector, really what you need to come to the table with is, first of all, some persistent backend. So that gives you some way of actually persisting the information that you're receiving through Egeria. You need to then implement basically something called the Open Metadata Collection Interface. This is what defines all the functionality provided by Egeria, things like creating, reading, updating, searching, and all of those sorts of things. I'll give you more detail on all of those operations in a few slides. And then finally, we need to make sure that we're exposing an API layer that mirrors Egeria's own APIs. So in fact, we'll talk about implementing this primarily through Java today. And that third piece you sort of get for free if you do it through Java, because you can leverage what's already there in Egeria. But in case you're using a different language, that would be a layer you potentially need to provide yourself as well. All right, so let's dive into a bit more detail on those. draw some pictures here as well to hopefully bring it to life a bit more. So first step here, I mentioned native repository connectors implement these repository level methods that are defined by the metadata collection interface. And these are really what provide that API level access to the metadata. So if you like, this outer white box is where you might need to implement your own API layer if you are not leveraging what's there for free when you're using Java. But in either case, you implement these methods that would ultimately be called by the API and that define those various operations, which we'll delve into in a few slides. Once you've implemented that interface, your connector code essentially is going to decide what to do for those various operations, those reads, those writes, those deletes, searches, and so on. And really that can run anywhere that connects to that API layer. So the example we'll walk through as sort of a real life example is a connector that we've written for a backend called XTDB. And that runs simply within the JVM, the same JVMs running the connector code and this interface. And then from there, what you're looking at doing is through the connector code is ultimately accessing that underlying persistence layer. So if you think about this in a very simplistic sort of hello world example, you could imagine that backend persistence layer. I mean, it could be as simple as files. More likely you would be using some kind of database backend. So, your connector code, when it receives a request to, let's say, create some particular object, you would then, write a row into a table within your persistence layer. And if a subsequent read operation comes in, your connector code would translate that read request into what table do I need to read out that particular object from. Again, very simple example using a very simple, let's say, relational database backend. So that ensures that all the information is then persisted, of course, within that persistent storage layer on the far right. So that's the very simplistic example of generally what's required to implement such a connector. What I want to do next is actually then sort of go to the next layer of detail and look at a real implementation of such a native repository connector and all the different things to consider as part of doing that. So as I mentioned, the example walkthrough uses a backend called XTDB. We have done a separate session on that specifically, looking at some of its unique characteristics, but as a brief recap, XTDB is a graph-based backend, and it is natively bitemporal, so it's able to handle things like point-in-time inquiries and so on, which is another interesting dimension of these interfaces. And it actually itself has its own configurable persistence layers. So that very simple example I just mentioned was using, let's imagine a relational database. If we look at a real backend like XTDB, as I mentioned, it's a graph store, but it actually is layered on top of backends that you can configure. So you could use JDBC backends like Postgres and so on. You can use Kafka, you can use S3 as a doc store, you can use various in-memory stores like RocksDB and LMDB and so on. And XTDB itself, in this example, it's actually written in Clojure, which allows us a fairly straightforward way of tying it into the Java ecosystem. So we can look at that as well once we get to that layer. So that's that last point. It does provide a Java API, which means that we can tie that directly into how we implement this open metadata collection interface within Egeria in order to implement these methods that ultimately provide the functionality for the repository. Okay, so let's look at the same schematics now with this real world example. Now, as I've mentioned, if you're using Java, and as I pointed out with this particular example, it has been implemented through Java, because we're able to leverage Egeria itself and specifically what we call the OMEG platform or the server chassis. This actually gives us a way of exposing those APIs without having to re-implement them ourselves. So really those APIs are calling through to a Java layer, and in fact, an abstract class, so an interface if you like. And all we need to do within Java then is override those methods within our connector and implement them in effect in order to provide that functionality for the connector. So that's indeed exactly what we do for this XTDB connector. That middle layer, where previously I talked about the connector code, in the XTDB world, what we're actually doing is standing up an embedded process inside the JVM, which basically serves XTDB's API, its Java API, which we can then call and have it take that information and then push it to whatever backends we've configured. Now those backends themselves, we'll see on the next slide, they could be running in various places. In fact, let me just skip ahead to that. So XTDB as a backend uses both a transaction log and a document store. It uses these to handle its own persistence and its own ability to sort of rebuild these read-only indexes and so on. Again, don't worry too much about the specifics of XTDB. The point is that it manages its own backend persistence that's configurable. And fundamentally, what we're doing through the connector is standing up this node that allows us an interface to those backends. Those backends could be running embedded. In fact, XTDB provides a purely in-memory based backend if you want to use that. It all runs embedded within the JVM of the node itself. Or you could connect these out to remote systems. So the transaction log could be running, in a Confluent cluster that sits out in the cloud. Your document store could be running on S3 out in a particular region of AWS, and so on. So there's nothing that says these persistence mechanisms have to be local to the connector itself. The configuration that you feed into the connector basically dictates where it looks for those particular backends. So hopefully that makes sense. But again, similar to what we saw in the very simple example, the fundamental point here with the backends are that those are what provide the ultimate persistence of the metadata for Egeria. So that is a real world example from a illustration perspective, but let's keep peeling the onion, keep delving into deeper and deeper layers. So again, this session is all about how to write one of these. So hopefully all of that covers sort of logically what the structure is, what's, let's say conceptually what's required to implement them. When it comes to actually writing one, there's really 4 steps you need to think about. The first one is identifying what properties are required for your particular connection. So if you think about that XTDB example I just walked through, I talked about things like configuring what kind of backend does it use? Do you want to use Kafka? Do you want to use S3? Postgres via JDBC, et cetera. So we need to feed in that configuration. I also mentioned things like the backend could be running on a remote system. It could be running in the cloud somewhere and so on. So you need to provide configuration details of how to connect to that. What host, what sort of authentication does it potentially need to do through, usernames and passwords or key pairs, all those sorts of things. So those are all the things you need to think about as properties that you feed into the connection in order to configure it. So that's sort of step 1. Step 2 then is we write something we call the connector provider. And we'll look at that again as we peel the onion in a bit more detail in a few minutes. But fundamentally, that's about providing those configuration properties into the connector to actually set it up. Then we need to actually write the connector itself. That's primarily about how we start up the connection and how we shut it down. So again, we'll look at that in more detail in a couple slides. And then again, I mentioned this a few times, but fundamentally to implement, let's say the real functionality of the connector, how do we create things, read them, update them, delete them, search for them, all that sort of stuff. That's by implementing this open metadata collection interface. And in fact, technically there could be a 5th step if we're not implementing through Java, which is again, implementing the API layer that exposes all of that through an API. But again, we get that for free in our example since we're using Java. Okay, so first step I mentioned, the properties for the connection. Let's look at that in a bit more detail. So I mentioned for XTDB, we want to look at what backend we would use for, let's say, the document store, the transaction log, and so on. There's other configuration where we actually have set up in the XTDB connector as well. It can run in both a synchronous as well as an eventually consistent asynchronous indexing mode, which could be useful for initial ingest, that sort of thing. So those would be some other configurations we would feed into it. Of course, if you're using your own backend, I mentioned some of these others, especially if you're connecting to, let's say, remote clusters, that sort of thing. You might want to look at the network address and protocol to access that backend, what sort of credentials are required, whether that's username, password, key pairs, etc. And again, depending on your backend, there might be other things that you look to configure. Other examples of performance characteristics or different modes it might operate in. You might look at configuring it for different levels of availability, all those sorts of things. So again, think about how you want to derive that through your repository. Once you've identified those particular properties, then step 2 is to write the connector provider. And I can flip back and forth between code here if we want, but actually what I'll probably start with is just embedded code within the slides, because then I can sort of describe it step by step, hopefully. But as I mentioned, the connector provider, fundamentally what we're doing here is taking those properties we've just determined from the previous step and then providing the details for those into our connector in order to configure it. So let's take a look at how to do that. So again, using Java as the example here, really what we do is we extend this base class, which Egeria provides, this OMRS repository connector provider base. And within that, we define a few different static members. Primarily, those are around things like a unique ID for this particular connector type, some descriptive properties about what this connector is, a URL to give you more information about it. And then what we have down here at the bottom, line 18 to 21, is some of those additional configuration properties. So in fact, for XTDB, we just take in a string which gives the whole configuration of which backends to use and how to connect to those and so on. For other systems, you may want to separate that out into different properties. It really depends on how you can configure it. In the case of XTDB, it sort of expects a particular string formatted in a particular way anyway. So the simplest for us here was just to send in that string directly. And then you see here, there are other properties, such as whether we want to use a synchronous index or not, since that was another property. We can configure the behavior of how the backend works. On line 20. So really what we're doing on 18 to 21 is just defining what those properties are, a name for the property, the configuration property and its type, and that's it. We're not really providing the values. These are more the variables, if you like. And then to define the connector provider itself, really all we're doing is defining a public constructor, which takes no arguments. And within that, going through a pretty standard set of steps. We set up the connector class name by just calling this connector class.getName method. We define a new connector type and set it up according to those various static members we had above, such as its type, its GUID, some of the descriptive names like qualified name and so on. And then we actually define what those configuration properties are for this particular repository. So we take those static members that define those variables, those property names, add those into a list, and then for the connector type, set this recognized configuration properties. So that's then able to articulate to anyone that wants to use this repository, what are the configuration variables, the configuration properties that can be set on this particular connector type. We then set that up as the connector type bean for the connector provider itself. So that's line 50. And then 52 through 60 are about setting up how we do logging for this particular connector through our audit logging framework. So that's really it for the connector provider. So that's, again, defining how this connector is configured, giving people information about that. So then step 3 is to actually write the connector itself. So again, think about this as sort of the next layer of the onion. To implement the connector itself, really what we're defining is primarily how it starts up and how it shuts down. So we're going to extend this class called OMRS repository connector. We're going to override a third method, which isn't directly startup or shutdown, but it's something called set metadata collection ID. This is how we define the instantiation of a new metadata collection. And the metadata collection, again, is that implemented code that says how we do all the real functionality, how we do the creates, the reads, the updates, the deletes, the searches, etc. So again, we'll take a look at that as the next layer. But besides that, what we're doing, again, is just the startup and the disconnect. So the startup and the shutdown. So let's have a quick look at that. So set metadata collection ID, you just have to withhold belief here for a second, or whatever the phrase is. Really, the logic here is this will be called as part of instantiating, as part of setting up your connector. It will receive a unique metadata collection ID. And what you're fundamentally doing here is just making sure that that is not empty. As long as it's not empty, you go off and create a new metadata collection. And again, this is what's implementing the true functionality to do the interesting stuff within the repository connector. We'll look at that as the very next step. But before we get to that, just to set up the connector itself, just some things to keep in mind. So again, it's about startup and shutdown. So we override the start method. And startup here, if you think about this from a repository perspective, this is about how do you actually take those values for the configuration properties that we just talked about with the connector provider. How do we receive those, and then based on those actually configure this connection, or sorry, this connector. So, if I sent in this case for XTDB, if I sent in configuration properties, which you can see being read here, let's say, for example, I want to use Kafka as a backend and S3 as a backend, then how do I go about setting that up? In fact, in the case of XTDB, it's fairly straightforward. I don't need within this code to try to reverse engineer that. I just pass the configuration that I've received. I just pass it on to XTDB, and the backend handles the configuration itself. But in your case, if you were implementing, say, a relational database as a backend, and that relational database sat in the cloud somewhere, from the configuration properties, you might retrieve endpoint details for it. So things like, what remote cluster is it running on? What credentials does it require? Pull that information out of the config properties. From that, then actually try to connect to that remote system. Make sure you're able to connect to it, because if you're not, you can't really start up the repository itself because you have no way of accessing the backend persistence. So that's really what the startup is about. In the case of XTDB, it does, some other interesting things. If I scroll down far enough here, for example, within XTDB, we use something called transaction functions, which means we actually take the logic of a lot of the operations, and instead of running them in memory within the connector itself, we actually push that code down into the repository, so that when an operation happens, we can execute it directly within the repository level. And it's sort of like pushing it directly to the back end. So to do that, we idempotently within the startup here, make sure that all of those transaction functions exist within the persistent store itself. So again, exactly what you do here in the setup will vary depending on your backend and exactly how you need to start it up and configure it. But that's fundamentally what this start method is about, is how do you start it up? How do you configure it? And then the last piece here for the connector itself is then how do you gracefully shut it down? So if you've gone through the work to stand up this node embedded for example, or connected to a repository that sits out in a cluster, in the relational database world, maybe you've spun up a connection pool, these sorts of things. Then at some point, if somebody's shutting this down or disconnecting from that repository, you don't want to just kill all the processes. You want to flush any queues. You want to, clean up the connection pools, these sorts of things, so that it's gracefully shut down, and you can avoid, potential data loss if you just crashed it instead of doing it gracefully. So that's the point of disconnect, gracefully shutting things down. All right, so those are the first 3 steps. Then the third step here, the one that is probably the most interesting, let's say, which I've mentioned a few times now, this open metadata collection interface is describing how the repository connector actually does the interesting work. So this includes all sorts of things. It includes how we manage the type definitions. So how we create new types as they're received, how we patch them, all those sorts of things, how we retrieve them, how we know what's implemented by that repository. It includes all the create, read, update, and delete methods for entities. The same again for relationships. It covers how we do creates, reads, updates, and deletes for reference copies. We'll talk in a bit more about what those are, if that doesn't make sense. It covers all the search methods. How do we search across those different things? How do we do classification? How do we classify entities? Covers re-identification in case an object needs to be rekeyed. Covers rehoming. Again, that's related sort of to the difference between homed metadata and reference copy metadata, which I'll talk about in a little bit more detail in a few slides. And then finally, it covers what we broadly call the graph methods. So how can we search across the repository and retrieve a whole set of related entities or interrelated objects, let's say, instances of metadata, without necessarily just retrieving them one by one. So there's quite a lot in there. That's each of these bullets is not a single method. Each of the bullets might be a handful of methods. So if you look at the actual code, you'll probably see, a good 30, 40 plus different methods that you potentially can implement. Now, it's worth pointing out that not every repository, even every native repository, will necessarily implement all of these methods. My general advice would be to work through them sort of in the order that they show here as bullets. In particular, I would say, graph methods would probably be one of the most complex and potentially one of the least implemented methods. But things like managing type definitions is, almost table stakes for a native repository to be able to successfully participate, as well as things like, creating and reading and updating and deleting entities and so on. So I'd work down the list from top to bottom as you sort of go through and iteratively implement a repository connector. All right, now, we have about 30 minutes left. That's not going to be enough time to walk you through implementing all 50 so methods in that respect. So I think what's probably more critical to walk through here is just maybe a deeper understanding on what those different concepts actually are and some of the considerations within those to think about as you're implementing a repository connector to support those different concepts. So these should broadly align with everything that we just saw on the previous screen. And we'll walk through these, one by one. So entities, relationships, classifications, I mentioned. Type defs is just a shorthand for type definitions. Again, I'll talk through the difference between homed metadata and reference copies. And we'll talk a bit about the importance of GUIDs and that the importance that they actually are unique. And then finally about something we call conformance and how that relates to Egeria repositories and specifically connectors like these. So let's take those in turn one by one. So the first key concept I would try to make sure everyone understands is entities. And very simply, entities are about describing a metadata object pretty much all on its own. So examples of this could be things like a business vocabulary term or a database or a field in a schema, a column in a table, all these sorts of things. If you think about representing metadata as a graph, then these you would typically think of as being the nodes or the vertices within the graph. So they generally describe things like concepts or people or places, things, that kind of stuff. So from a repository perspective, you might think of these as sort of the primary, most fundamental core sort of instances of metadata that exist, and that you would ultimately want to persist in order to be able to serve it back. The other key concept then is relationships, and these are about describing typically a directed association between two entities. So example of this might be the semantic meaning of a database column. So you could represent this by taking a business vocabulary term, which as we just saw could be one entity, and then relating that to a relational database column, which could be another entity. And by creating a relationship between those two, what you're really doing is describing what that database column means by saying it means this business vocabulary term. Now, it's important to note that, well, first of all, in a graph sense, if we draw this analogy again, the relationships you can probably imagine would then end up being the links or the edges within the graph, and they show how those different nodes or vertices, the entities, how those are related. What's important to note here from a repository implementation perspective is that these edges themselves can also have properties, specifically properties that describe that relationship itself. So if we take this example of a semantic meaning relating a column and a term, you might imagine other properties on that relationship, like say maintenance details. So who created that relationship between the term and the column? When was it created? You could imagine other properties like confidence details, percentage indicating how confident we are that that really is the meaning for that particular column, especially if it was, assigned by a system or, somehow automatically inferred, and that's what created this relationship rather than a person. So just keep that in mind as you're implementing a repository, that relationships are not just a link, but they do have properties on that link as well. Okay, so going on to the next key concept then, classifications. These are really about providing a means for extending an entity with additional facets of information. So traditional example of this would be something like describing the confidentiality, or if you like, the level of information sensitivity of a particular entity. So for example, you might say a database column should be treated as sensitive information. Other classic examples would be things like PII or sensitive personal information, SPI. These would be different ways of classifying those entities, like a column, to say how the information should be treated. So I tend to think of these as really providing additional attributes of an entity, but in a way that can be used to identify a number of different entities that are all similar in this specific aspect, like information sensitivity, confidentiality, and so on. Now, it's important to note here that even though these sound like just an extension, just an additional set of properties on an entity, when you come to implementing this within a repository, it's worth thinking about some trade-offs here. Today, and these classifications can only be accessed or updated via the entity within Egeria. So in terms of the interface, the metadata collection interface, you can't really create or do anything with a classification without touching the entity at the same time. So you might think, okay, well, I will just store them in the backend as part of the entity. What's key to consider, and by the way, that could be the most performant way of doing it, because every time they're retrieved, you're retrieving it through the entity. But what's important to consider is whether that gives you the necessary level of flexibility in some other respects. So what you'll see with classifications is that you can also apply things like effectivity dates. And that means you could have the same classification applied to the same entity multiple times, but only being active at different points in time. And therefore, if you're only storing it as part of the entity and not distinctly, you either need to handle that sort of multiplicity dimension directly as part of your persistence, which could add some complexity there for you, or potentially make it easier by storing classifications as something distinct, and linked through to the entity through something like traditional primary key, foreign key relationships, with the potential trade-off that doing it that way may have a performance impact. So just some trade-offs to consider and maybe experiment with as you implement a native repository to figure out how best to address those. All right, so that's classifications. The other key one that I mentioned, type definitions, or type defs for short. These really define the structure of each metadata entity, relationship, or classification. So for example, we've talked about things like business vocabulary, things like columns in relational database tables. Type defs are what define what those are, what properties can be stored against them, how they relate to other types as well. So for example, let's say a database schema inherits from an asset type def. So an asset type def has a certain set of properties which then a relational database schema extends rather than having to reinvent all that same set of properties, which are shared across all other assets as well. So those are quite key to note. And what's important here really with type defs, the reason that these exist are that they give Egeria a general way of describing those different metadata types without having to strongly type them directly into the APIs. So what you'll see in the metadata collection interface, when we come to that in a few slides, as you implement these methods, really what they're receiving and sending, returning and so on is fundamentally just an entity or a relationship or some collection of those, but they won't be directly interacting with, say, a database schema or a glossary term or, relational column. And so that's where type defs come in. They give us a way of defining what those more detailed properties are, but in a way that we don't have to change our APIs and our interfaces every time we add a new type or change what those types look like. And again, this is specifically at the repository level, since we're talking about repository connectors. So the repository level is very generic. It just works on entities, relationships, and classifications, and type defs to generically define what instances of those look like for the different types. Hopefully that makes sense. So let's keep going with key concepts. The other key concept here from a repository connector perspective is to understand the difference between homed metadata and what we call reference copy metadata. Fundamental difference here is that anytime an instance of metadata is created, whether that's an entity, a relationship, or a classification, it is created in one repository only, and that repository is called its home repository. As long as you're interacting with that instance in the home repository, it is changeable, it's modifiable, it can be updated, it can be deleted, and so on. And it's worth mentioning as well, from a distributed solution perspective here, that everything can be independently homed and still interrelated. So for example, you can have address as a, say, business vocabulary term. That's an entity that could be homed in repository A. You can have ADDR, if that's, say, a database column, another entity, that can be homed in another repository, say B. Then you could have a confidentiality classification, and that could be applied to that first term, the address term. But the confidentiality classification itself may not exist in repository A, it may exist in repository C. And then finally, you could have a semantic relationship that exists between the term and the column. So that was repository A and repository B, but that semantic relationship itself may exist again somewhere else again. So may exist in repository D. So it's important to recognize that one repository may not have the holistic view of all of these different objects for a particular instance. And therefore that you need to, that's really where this concept of homed and reference copy that we'll talk about in the next slide comes into play, to make sure that even though these can be independently homed and independently changed, we are still able to interrelate them, but we minimize as much as possible the risk that the same object is changed in multiple places at the same time. So by removing the possibility of that occurring, we have much greater control of the metadata ecosystem itself, ensuring that things don't diverge and suddenly there's a loss of trust in what's correct and so on. And so again, from my perspective, this is really the unique power of Egeria, is the ability to sort of define this, what I call protocol semantic. So really the ability to federate this metadata across a distributed landscape. Okay, hopefully that makes sense. So that brings us to reference copies. So if homed metadata is the mutable copy because it's where that instance is uniquely managed and only in that location, to support the ability to keep those independent pieces managed in different places, but still allow them to be linked together, we also need to at least be able to share some minimal sort of stub, if you like, or what we call a reference copy, which is a bit more than a stub, but we need a way of storing some reference copy, some copy of that information in a way that those linkages can be created. And that means, again, to make sure that we can reduce, minimize the impact of people changing the same information multiple places, these reference copies we make immutable wherever they do exist. So that's the key difference here between homed metadata and reference copies. And we saw earlier when we talked about the connector, this concept of a metadata collection ID. That unique ID is really what drives and determines whether something is homed or a reference copy, because every instance of metadata, whether it is an entity, relationship, or classification, carries with it its home metadata collection ID, and every repository, by implementing the metadata collection interface, defines its own unique metadata collection ID as well. So you'll see in the implementation itself, you can confirm whether something is homed or a reference copy by comparing what is in the header of the instance itself with what your own repository has as its home metadata collection ID. If they match, it's a homed instance, you can mutate it. If they don't match, it's a reference copy and it should be treated as immutable, other than the interfaces that specifically allow things like creates and purges for reference copies. Okay, so that's reference copies. I think there's just two more concepts to go here. The next one is GUIDs. So I think most folks are probably broadly familiar with what a GUID is, a globally unique identifier. To make these different protocols we just talked through, truly viable between homed and reference copy and so on, as well as the way that these different objects are exposed through interfaces like retrieval, we do expect every metadata instance to have a unique identifier. And we do expect that to be a proper globally unique ID. Now, we don't mandate the use of a particular algorithm to do that. So you could, in theory, use any algorithm you like. But the key point here is that there should be an infinitesimally small chance that any two systems would end up creating the same GUID. So I would certainly strongly suggest reusing algorithms like UUID's random ID, or random UUID rather. And that's because those sorts of algorithms carries, I think the numbers are something like you could generate 1 billion of them a second nonstop, and it would still take you close to 100 years before you would potentially, have a high chance of reaching a conflict. So my strong suggestion would be, unless you have a really, 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 really compelling reason not to use a UUID, the simplest is probably just to use a UUID, especially for these native repository connectors. But again, not mandated if you do have a really, really compelling reason to use something else. Okay, then finally, from a concepts perspective, want to talk briefly about conformance. So conformance is really what we call the way of testing and ensuring that a repository adheres to all of these different concepts and behaviors that we've just briefly touched on. And what we provide as part of Egeria is something we call the conformance test suite. It's an automated testing suite that leverages these APIs, these metadata collection interfaces, to run through a repository, like a native repository connector that we've been talking about here, and test out that it is conformant. So it will go through all the create interfaces, the read interfaces, the update interfaces, the deletes, the rehomes, the re-identifies, the searches, and actually create information in there and then test it and be sure and make sure that it behaves the way that's anticipated by these different concepts and interfaces. If it does, we say it's conformant. There is actually a mark you can get as well to prove that your repository adheres to the standard in effect. So that's another great way of sort of testing as you go along, as you're iteratively developing your repository connector and ensuring it's behaving the way that we expect. Okay, so we've got about 10 minutes left. So I just want to go through a few other sort of gotchas in terms of implementation. Then I can open it up in case there are questions, other things folks want me to delve into code-wise or so on. So in terms of gotchas, caveats, one other one to be aware of that may not be immediately obvious is within Egeria, we support the concept both of versioning and of history. And I certainly am happy to put my hand up and admit that initially I thought, well, aren't these the same thing? What's really different about them? So I thought probably worth covering that for others as well. In my mind, the simplest way to think of this is really that versioning is really a way of tracking that something has changed, but not necessarily tracking the change itself. So in very simple terms in Egeria, we do track a version number on metadata instances, but seeing whether something is a new version or not is really just about seeing whether that version number has increased. Now, I would contrast that with history, which is really more about retaining a record of the change. So, this isn't just about seeing that a version number has increased and therefore we know something has changed, but not what has changed. History is about saying, this particular property changed and its old value potentially used to be this, and the new value is this, and here's when it was changed, here's who changed it, so on and so forth. So history provides a much, much deeper record of that information. And there are different ways of implementing that, obviously, within a backend as you think about implementing this within a repository connector. But the key point here with history, the key difference is that you can reconstruct what metadata looked like at some historical point in time. If you've never tried to implement this, you may think it's fairly straightforward. I can tell you it is significantly more complicated than you might initially anticipate, but certainly more complicated than versioning, just seeing that a number increases. So do bear in mind as you're implementing a repository connector, whether you're only supporting versioning or whether you intend to support history. You'll see most of the methods within the metadata collection interface, maybe not most, but quite a number of them take an optional time argument. An optional date argument, which would give you this point in time inquiry capability. And that requires history, not just versioning. Okay, so one thing to remember there. In fact, that's what I just mentioned. So many of those methods that you would override in the open metadata collection interface, they take a date argument. That's fundamentally because we designed Egeria from the beginning to handle history and not just versioning. So we can do those point in time inquiries. One last comment on that. As I mentioned, it is significantly more complex than you might anticipate. And that's not just technically how do I store these things or how much volume might be created and so on, but also understanding what I call here the nuances in bitemporality. So this comes to the differences in things like transaction time versus business time. So you may only learn about something that happened in the past sometime after it actually happened. So there's really two dimensions to that history. When did you know about it, and when did it in reality actually occur? And how you apply those can cause some complicated conceptual understanding and so on. So my personal recommendation would be very much so if you're planning on supporting history, to look at some backend repository that already has some kind of native support for that. So in this example, we've been talking about with XTDB. That is a repository I mentioned earlier that does natively support that bitemporality for history. And therefore, it makes it quite straightforward to use it as a backend and implement history through it, while abstracting away a lot of that other complexity you otherwise have to worry about. And just to give a flavor, we're talking about things like if you need to retrieve, say, an entity and its relationships, but you're doing that at a point in time, say, 3 months ago. You don't just need what are the properties of that entity 3 months ago. You also need what did all of its relationships look like 3 months ago, and what did the other entities at the other ends of those relationships look like 3 months ago. So you almost need, an entire understanding of the ecosystem 3 months ago to reconstruct some of these methods, not just a singular record history, if that makes sense. You need all the referential integrity intact at a particular point in time. So hopefully I haven't totally scared folks away. The nice thing with repositories that do natively support this, like XTDB, is that they take care of all of that referential integrity for you. So you don't have to worry about having to figure out how to reconstruct it. And then I know we're nearly out of time here. So the other key one from a gotcha's perspective here is just some tips on if you have questions about how the repository is supposed to behave. There are a lot of nuances, potential edge cases to think about. So this is the general hierarchy I would suggest as you're implementing such a connector to figure out, if you have a question, you're not sure exactly how something is meant to behave in a particular scenario. First one is to check the Java docs of the open metadata collection method. We do try as much as possible to reflect any additional detail into those so that they are, easy to self-serve from. The second one, if you're not finding what you need there, is to actually look at an existing implementation, whether that's the in-memory repository implementation in Egeria core itself, the XTDB connector we've talked through here, or the Janus graph connector. You're still not finding your answer there, or it might be complicated to try to read through that code. Perhaps the easier way to go would be actually just running your repository connector through the conformance test. That should identify, in most cases, where things don't behave the way that we might expect, or if it does pass, then it's a reasonably good check that your repository is behaving the way that we anticipate. Only caveat there is that there may be certain edge cases we've not yet put into the conformance test suite. So, there could be some, let's say, false negatives there, or sorry, is that the right word? You could have things that look like they're succeeding, but actually it's just because we haven't yet put that edge case into the conformance test suite, and it may not be behaving the way that we would ultimately desire. But that should continue to improve over time, the robustness of that. The fourth area to look then is in the documentation itself. So if you go to egeria-project.org, that's where all the docs are for Egeria. And then finally, of course, if you're not finding your answers there, when in doubt, raise a question, whether that's on Slack or via a GitHub issue. Certainly myself, as I've gone through and implemented connectors like XTDB, I've gone through, say the first 3 and not found, or in fact, all of those not found my answer. And then, we've had an internal discussion to conclude on exactly how we want particular edge cases to be addressed. Hopefully most of that's worked out now, having now implemented a repository that supports every method of the metadata collection, but just in case, those are the best places to go.
So when you say an internal discussion, you meant a community discussion, I guess.
Absolutely right. Sorry. Yeah,
it's okay.
Absolutely right. That was everything that I thought I could get through to try to help people as best I could with a repository connector in an hour. So I had 4 minutes to spare. Is there anything else that you'd like me to maybe dive into code-wise or other aspects to discuss? Anything else you want to bring up now?
I haven't got anything. I really liked you communicate really simply and in a really clear way, and going through these concepts. I think it was really nice to hear them said so clearly. That's what I really liked about it. So I hope this that when we have the recording, people will look at it, and it's a way to get another way to get a handle on some of those basic concepts around Egeria.
Yeah. I figured if I dived straight into code, I would probably lose the whole hour talking about 3 methods. We wouldn't necessarily get a very broad go of it. So
that was good.
Cool.